Hi, everyone. So today we're going to be talking about our first parametric model, which is the basic linear regression model. This is an extremely common model. It's often the first thing you'll use when you're going to analyze new data and you want to kind of understand the relationship. Even if your data falls under the case of having an X variable that's binary, that takes values of 0 or 1, like we were looking at in the first class. Even in those cases, people often start with a linear regression model because it's flexible enough to accommodate that, but also so much more. So linear regression, before we get into it, let's do our standard things. We're going to want to make sure that we have tidyverse loaded up. We're going to want to make sure that we have ggplot loaded up. And for this lecture, we're going to be looking at a new data set. So you should have access to that on Quarkus. The name of the data set is violent crimes data. So we'll go ahead and find wherever you've stored that. Okay. And we can kind of copy this middle bit of code here to just get kind of the reading in of the data part of it. Okay. Let's run that. Okay. So what's the first thing we do when we read in a new data set? We want to take a look at it. We'll also take a look at the code book, right? So here's violent crimes data. What do we have? We have year, so 77 up through 99. So these are 1977 all the way up through 1999. Then we have some other things: VIO, MUR, ROB. So this is violent crimes. I think per capita, or no, per 100,000. Yeah, definitely per 100,000 members of the population. And then murders per 100,000, robberies per 100,000, incarceration should also be, yeah, per 100,000. Okay. Then what else do we have? We have state ID over here. So that looks like it's a discrete variable. So state ID, this is the United States, so we should be seeing 51 of these states or more, depending on if the kind of territories are included. So we can take a look at that variable. Then we have this variable shall. What is shall? Shall is equal to 1 if the state has a shall carry law in effect in that year, and 0 otherwise. Okay. And we'll talk a little bit more about that soon. Okay. All right. What else do we have? We have these variables here, which all look to be like continuous variables. Average income is what this seems to be. And indeed, when we look at the code book, it's real per capita personal income in the state in thousands of dollars. So 1977 in state with ID number 1, we have per capita income of about $9,563. Okay. So, all right, that's kind of what our data looks like. One thing that we might be interested in is exploring the data in the same way as we did for discrete random variables, but now we have continuous variables. So how do we kind of explore the data? In this case, we can't use a histogram because there's going to be too many values, and we can't just kind of tabulate up those values. So we'll use a new type of plot, which is a density plot. So, but first things first, we'll filter our data so that we drop any NAs. Oops. Okay, so what did I do here? I accidentally created a data set that's a name that I didn't intend. So you can actually use the rm command, remove, to get rid of any kind of mistaken variables that you create. Okay, so DIT is what we want. Actually, this is identical to the violent crimes data file that we inputted, so there's no missing data in this data set. So that's nice. Now let's look at one of our continuous random variables. So we'll use geom density instead of geom bar. Just like with a bar, the only aesthetic you need is an X value. With a histogram, you count up how many times each X value appears. But recall, like I said, with a continuous random variable, each value probably only appears once in this 1173 observation data set. So that won't be very useful to count the unique observations of each value. Instead, we'll use geom density. And what this is going to do, it's going to create kind of a smooth plot. Let's take a look. A smooth plot where, again, average income would appear on the x-axis, but on the y-axis, instead of distinct bars, what we have is kind of the approximation of a probability density function. So at any sort of given point, if it's higher on the y-axis for a particular value of average income, that means that there are more people with having average income around that point. And if we look at the area under the curve, just like with our normal distribution, that would give us the probability that someone has an average income less than or equal to whatever point we picked, right? If we look at kind of the area to the left of that point we pick, right? Perfect. So that's for average income. What else? We have so we do have this data on violent crimes per 100,000. So this also looks like a continuous random variable. So let's take a look at that as well. Okay. And so what does this look like? Another kind of density plot. What we can see is if we look at kind of the area to the left of 1,000, that's most of the area under the curve. So that's kind of saying most states in most years have fewer than 1,000 violent crimes per 100,000 people. However, when we look to the right, we do see that there is some positive density with these high values. So there are some states in some years where the level of violence is quite high. Okay. So, should these be called outliers or not, as we define them in class? Well, we can do some regressions and see what will happen if we keep those values or if we get rid of those values. Okay. So we have average income and we have violence. So one thing that we might want to do also is plot a scatter. So geom point is going to be the scatter plot of points. And here our mapping, our aesthetic for our X, we're going to be thinking about average income as the X variable. And we're going to be thinking about violence as the Y variable. Okay. So our analysis here is going to be thinking about, do changes in average income lead to changes in violence per capita? Okay. And when we say changes in average income, our unit of observation is a state in a particular year. So if we, kind of vary the level of average income, say by like going to a state with a higher income, will that lead to a different level of violence, right, per capita? Or within the same state, if the income increases between one year and the next, would that lead to a different level of violence per capita in that state? Okay, so that'll be kind of the question we're exploring with this data. So let's take a look at the scatter plot. Here's that. So we have an average income on the x-axis, violence on the y-axis. Each point corresponds to, again, a particular state in a particular year, the level of average income and the level of violence per 100,000. Okay. Yeah, and just like we saw with the density plot, we can see most observations have a level of violence that's below 1,000 per 1,000 incidences of violent crime per 100,000. But there's some states that have a much higher level. Okay, cool. So let's run a linear regression. We'll assign the linear regression to this variable reg1. And the command for the linear regression is LM, standing for linear model. You can see in the linear model, you're prompted for a formula and data. Okay, so what formula should we put in? Well, the formula is exactly the same sort of style as the formula for the t-test. So we want to have our y variable, in this case violence, and then tilde our x variable. Okay, and just like before, we'll have data is equal to our data set that we're using. So when we run that, what do we get? We have some new thing has appeared in the global environment. And there's a bunch of different stuff here. Importantly, we can see there's coefficients. So we can see our intercept and our coefficient on average income. So our beta 0 and beta 1 estimates. And there's a bunch of other stuff, which we don't need to think about right now. Okay. So there's reg 1. Now, if we want to take a look at it in kind of a nicer form, we can use the summary command. And when we take the summary, we see a bunch of information. So let's go through it one line at a time. The call gives what basically just what we wrote for our linear model. And it's that violence is being regressed on average income using data from DAT. Residuals, what is a residual? Residual is the difference between the predicted value of y for a given x in our data and the actual value of y, right? So it's the difference between what our model predicts and what's actually happening in the data. Okay, so we have this residual, we have some information. So the smallest residual, we're over predicting by 687 because our prediction minus the actual y is negative 687. And then, on the other end, that's not that important. Don't have to pay attention to that 99% of the time. What you should pay attention to is this table, this part of the table here. This is the most important stuff. So we have our estimates for the intercept, beta 0 hat, and our coefficient on average income, beta 1 hat. We have the standard error for each of these things, right? We have the t-value. What is the t-value? The t-value is just the estimate divided by the standard error. That's it. The t-value is t actual from our data for this regression, assuming a null hypothesis of 0. So it's going to be estimate minus 0 divided by standard error. That'll always give you this. And then this probability, this is the probability that z is kind of greater than absolute value of t. So this is just our p-value. So you can see here that the p-value for both of these estimates is quite small. So the chance that we would have observed, a coefficient of 53, if the true coefficient was actually 0, well, the chance of that happening is less than, it's infinitesimal. So we reject the null, right? And we can see that there's these stars. So these stars correspond to significance levels. So if there were 1 star, it would mean that the p-value is 0.05 or less. 2 stars means the p-value is 0.01 or less. If it's 0.01 or less, then by definition, it's going to be 0.05 or less, right? So if it's 2 stars, then that's stronger than 1 star, right? Everything that's 2 stars is also 1 star as well. 3 stars means the p-value is less than 0.001, right? So less than 0.1% chance of observing the coefficient we did if the null is actually 0. Okay, so we have 3 stars here. That makes sense. Both of these values are less than 0.001. Okay, and that's it. How do we interpret the coefficient? What does 53.387 mean? Well, recall that average income is in terms of thousands of dollars, right? So if we increase average income by $1,000, so by 1 in our data, right? Then the level of violent crime per 100,000 people will actually increase by 53.4. So an increase in average income by 1 unit, which corresponds to a $1,000 increase, will lead to an increase in violent crimes per capita of 53 per 100,000. Okay. All right. So that's the finding there. What else might we want to do? So one thing that I ask you to do in the homework is to predict the level of violent crime for different levels of, predict the level of Y for different levels of X. So if I give you a level of average income, I say, hey, here's a state with an average income of, $10,000 per capita, then what would be your prediction for the level of violent crime in that state? So how do we do this? Well, if we wanted to do it by hand, we would take 10, our kind of X value that we're wanting to predict at, times 53.387. And let's just kind of be, so we would have 10 times 53.387 minus 229.657, right? So that's our X times beta 1 plus beta 0, right? Or if you like better kind of in order, we have beta 0 plus X times beta 1, right? So we would predict 304 violent crimes per 100,000 people in a state with an income of $10,000. If we want to do this for multiple X values at once, we can do that. What we need to do is create a new little data set with all of the X values that we want our model to predict a Y value for. And we're going to enter that into a little table using the tibble command. And our tibble is going to have one column, which is just different levels of average income that we want to predict for. And how do we list different levels of average income? We use the C function. So C means concatenate. So let's say we want to predict at 10,000, 12,000, 14,000, and 16,000 per capita. So we create this new data, and then we use the predict command. So what does predict want? It wants our regression in order to actually compute the predictions. And then it wants the data that we'll be predicting at. And what we can see is indeed for kind of that $10,000 state, we predict the same level of violence as we did when we did it by hand. And then here's our predicted levels of violence for the states with higher income. Okay, so we've run the regression, we've interpreted the coefficients, and we've predicted different values predicted different values of Y corresponding to kind of some X values that we chose. Okay, perfect. So what can we do next? So maybe one of the things we might want to do is on our scatter plot, we may want to plot our regression line and kind of put the formula. So someone could look at this plot and look at our formula that we estimate and interpret everything all together all at once. So let's take a look. We'll start with the same geom point. Right? So that's going to give us these points on the scatter plot. And now we want to put a line on top of it. So what's the kind of object for a line? So it's a computed object. It's not just from the data directly. R will need to calculate it using the lm command. So we'll use stat smooth, and we'll say the method is lm. So we want it to do a linear model. And the data that we need is the same X and Y. And the last thing we need to enter is that we don't want it to display standard errors. So I'll show what happens if you don't have that in a second. Okay, so let's take a look. Oh, average not found. So I made a little typo here. Okay, so that's what that looks like. We can see it's a positively sloped line as we expect, right? Given the regression output that we have, right? Now, if we want to add the regression formula, well, we know how to add text to a plot. We use the annotate command. So it's going to be a text. And then we need to find a place to put it. So it looks like maybe at 13 and let's see. Yeah, maybe like 2750. And our label, well, it's just going to be our output from the regression, right? So I'm reading this off of the estimated regression output, which I got from the summary command. And that's it. Let's take a look at this. All right, very nice. Okay, so we can see blue text corresponding to the blue line. That's our kind of complete regression formulation. Okay, perfect. Of course, we can always clean this up, make it look a little nicer, right? So what might we want to do to improve readability? Improve our axes, right? So average income is kind of interpretable. But let's make it even clearer. So average income in thousands of dollars, thousands of US dollars. Our Y label, violent crimes per 100,000. Okay. I like classic. Let's take a look now. Okay, it's looking a little better. One thing is it's a little bit hard to see the regression line. So maybe we can improve that. One thing that we can maybe do is change what the points look like to maybe make them kind of fainter. Let's see if this works. Yeah. So that kind of like makes the points a little fainter. So we can see that the line pops out a little bit more. What is alpha? Alpha is the level of transparency. So the smaller is alpha, the more transparent your object, whatever you're plotting, is going to be. Okay. All right, so that looks pretty good. You can kind of leave that. All right, what should we do next? So one thing we could do next is we could repeat this exercise, but maybe dropping the outlier points. So it looks like these points that are all very large, that are bigger than 1,000, there's kind of like, this sort of string of points in the upper right. So, we need to decide, are these outliers or not? But just to see, like, how would you run the regression if you were dropping them? Or how would you display this data? So what do? We create a new data set, which is the filtered version of the old one. And we want only levels of violence that are less than or equal to 1,000. And you can see that we've dropped about 50 or so observations, right? So we can run our regression exactly the same as before, except using DAT2, which is the filtered data that's dropped these higher points. And summarize that. You'll notice that the average income coefficient has dropped by more than half, right? So instead of a $1,000 increase in average income leading to 50 more violent crimes per 100,000, it's only leading to 25 more violent crimes per 100,000 when we drop what looks like maybe this outlier, right? I definitely encourage you to look at the data and see, are these violent crimes that are kind of high in the upper right, are these all from one state, right? In other words, is there kind of one state that's an outlier? If so, if we kind of drop it, then this relationship is the one that holds for states apart from this one, apart from this kind of outlying state, okay? But that's for your own personal interest. We can replicate our analysis using with the full data set, except now using this truncated data set. So the only thing I've changed is DAT2, right? I've kept everything else the same, except now I'm also going to change the annotation, right? Because that was for the old regression. The new regression is 106.56 plus 25.61 average income. Okay. So when we plot this guy, we can see this is much, much flatter of a relationship, right? Okay. Last bit. What should we do? Let's think about a linear regression with a binary X variable. Okay. So this variable that I mentioned earlier, shall. So shall is equal to 1 if you have a shall carry law, which is a looser gun law. So I encourage you guys to look up what is a shall carry law. But shall carry law equal to 1 means looser gun laws, right? So now we can think about, okay, does the presence of looser gun laws lead to more violence or less violence in a simple regression? Okay, so let's take a look. So again, we're using violence as our y variable, but now we're regressing it on shall. We're using our full data set, not the truncated data set. Okay, we run this regression. Summary. What can we see? Well, here it looks like shall has a negative effect. So if we go from a state with tighter gun laws to a state with looser gun laws, it looks like there's actually a reduction in violent crime. Right? Is this causal? Probably not. There's probably a lot of things that are different about shall carry law states compared to non-shall carry law states. Also recall the time period of the data set we're looking at is 70s, 80s, 90s. And that's a time period when large American cities are having kind of extreme levels of violence. But these large cities tend to be in more liberal states that restrict gun use and gun ownership, right? So not a causal relationship, but we do see that there is this correlation between shall carry laws and the level of violence, okay? One thing I want to point out, one thing that I kind of talked a little bit about in lecture and that I want to point out here is that we have a beta 0 and a beta 1, right, for this regression. And we see that negative 1.161 is highly significant. So that would suggest that if we look at a difference of means between a shall carry law states and non-shall carry law states, that difference should also be highly significant, right? And indeed, that difference will be negative 161, right? So let's group by shall, and let's summarize, take mean violence. And what we're expecting here is that for the group with shall equal to 0, that group is going to have a mean level of violence that's equal to the intercept in our regression. And indeed, that's what we see, 542, right? Why is that the case? Because in our regression, remember, we have y equals beta 0 plus beta 1 times x. And when x is equal to 0, right, shall is equal to 0, that's just y equals beta 0, right? So for our shall group, our shall with x equal to 0, their average level of y is just going to be beta 0, right? We should also see that the difference between these two things, between these two means, is equal to the regression coefficient. When we take 381 minus 542, indeed, we see negative 161, right? So we do see that the regression coefficients map to the mean level for the x equals 0 group, and then the difference of means for x equal 1 minus x equals 0 group as the coefficient. Okay. Perfect. So that's it for this week. I think that should give you everything you need to do this week's homework. And yeah, I will see you guys in class, in tutorial, and in office hours. All right. Bye.